So do you recall the electromechanical impedance technique? Now it seems that you have a basic understanding of the global vibration technique because you have been doing the experiment also. So the EMI technique is similar. It also works on the vibration principle. But then the difference is that in the case of the EMI technique, we are externally actuating the structure. The actuator is there in the form of the piezo patch, which actuates the structure by external excitation voltage, and that acts as means piezo patch is acting as actuator, and then by the property of the direct effect, it's acting as sensor also. So both ways it's acting, and what we are measuring here, we are basically measuring current flowing through the circuit, which gives us the measurement of the admittance. So admittance has both the phase information as well as the magnitude information. So accordingly it has two components, G and B, conductance and susceptance. So here we saw that essentially this is also a vibration based technique, and we had done the compare and contrast with the global vibration technique also. Let me just go to that particular slide where we had done the compare and contrast. So essentially in the case of the global vibration technique, we are using shaker or we are using hammer. Alright, so here we are using the same piezo patch as the shaker also. So essentially this is also vibration based technique, but it does not involve separate actuator and sensor. You don't need hammer, you don't need shaker. So piezo itself will act as the shaker and it will apply sinusoidal voltage. I mean, we are applying sinusoidal voltage across the piezo, and this will actuate the structure into harmonic vibrations, and we are gradually changing the frequency, so it's a sweep kind of vibration pattern. So here basically we are measuring not in the terms of acceleration or displacement or strain. Here we are measuring an electrical parameter, the admittance. So that is also like an FRF because we are applying some kind of excitation and then we are obtaining response. So here we are obtaining the data directly in the form of frequency domain. In the case of the global vibration technique, you are first acquiring the data in time domain and then you are converting into frequency domain. That involves laborious computation. Then you have to use the peak picking method to get the mode shapes, etc. So here we are essentially obtaining the FRF, but we are obtaining FRF directly. So after this we had described two case studies, one involving concrete. I hope you recall that. So what we find is that when the damage occurs, then because in the case of concrete, first phase of damage is in the form of micro cracks, so the signatures, they do undergo change, and then after that there's a region where we don't see much change in terms of the deviation in signature unless we are reaching a penultimate stage. So penultimate stage, there is a very large change. So at the penultimate stage, just before the collapse, we could see something very large. So after this, we also went on to tests on prototype structures of a scaled model of bridge, and here we could see that the piezos, they have a zone of influence in the case of the reinforced concrete. So zone of the influence means that every patch, essentially it has an area of radius, say maximum 100 to 200 millimeters, and within that zone it identifies the occurrence of cracks, but beyond that zone its influence is not there. Alright, so this we had seen. through the experiments and the data which I presented. So this after the first cycle, there were cracks near piezo patch number 5 and 4. So they have shown change. 3 has not changed and 7 has not changed. Because now you can see some of the cracks, like a crack is just passing very close by patch number 5, and near patch number 3 there is no crack, but yes, in the next stage there would be some crack near patch number 3 also. So now there new crack has occurred near patch number 3. So now you can see this crack.
Sir, I had one question here.
Yeah.
Sir, what is mean by partial slip at previous slide?
Slip is referring to the strain gauge. See, the problem with the strain gauges is that near the failure strains, the debonding process occurs. See, when the strain level is less, at that point there is a near perfect value. Whatever is the strain in the rebar or whatever is the strain in the concrete surface, same is reflected in the strain gauge. But what happens is that after the contact is broken, then what will happen is, even if the structure undergoes large strain, it will not be transferred to the strain gauge. So that is called a slip. Okay, now we come to another case study. We have only one case study left, and the purpose of that case study is to just observe what is the sensitivity of damage detection of this technique. So this study was done for identifying seismic induced damage in reinforced concrete structures. So for this purpose, this was a model frame, a 2-story model frame, and this was being done by another group which was basically monitoring this structure using global vibration techniques. So here I was also a participant, and I had installed 2 sensors. You could see here one piezo patch near the mid span of the second floor beam and one patch near the joint here in the first floor beam. I hope you can see both these patches. Now this patch number 2 was not positioned exactly at the midpoint, the reason being that there was some other instrumentation near the midpoint, so it was a little bit off the midpoint. So this is the setup here. Model reinforced concrete frame with raft at the bottom. So this was a scaled version. So this was subjected to vertical vibrations. So it was excited, and after the excitation, the period was given to the motion, and then in this time the recordings were made. The recordings were made using the EMI technique as well as the global vibration techniques. Global vibration techniques, they were handled by another group. So we had done the measurements which we call baseline measurements before starting the experiment, and after giving some jerk which was in the vertical direction, the time histories are shown here, we again recorded measurements from the 2 patches, that is state 1. Then another excitation was given. After the excitation, measurements were made. So this way continued data points were made. So total 7 states, we define states as the intervening period in between 2 consecutive motions. So that's how we had done the recording of the data. And now I will show you how the data varies. So first I am showing you the signatures of patch number 2. Patch number 2 is here at the second floor, bottom soffit of the second floor beam. So what you observe here, that initially the signatures, they are undergoing change. Just give me a minute. I have to put my phone to silence. Oh, okay. Sorry for that. So now here what you can observe is that the visible cracks were at this state, and this is state number 6. But then the piezo patches, they were giving us indication at state 5 and 4 also. We are getting some indication from the piezo patches. So this is the location of the damage which was near patch number 2, flexure crack which originated from the bottom of the beam and it went up. So after that, what happened is that after state number 6, what we found, the signatures were showing something unusual. For example, in the beginning we are seeing that the signatures are following some pattern and there is an upward shifting with damage, but suddenly we found that 7 and 8, the signatures were very peculiar. They started coming down. Later on, we found that the patch itself is broken. So patch was found broken in state number 7. So today we'll also see how we can do the diagnosis of the patch itself. Diagnostics is very important because we are relying on the sensors. So if the sensor itself is damaged, then our data will not be reliable. So we'll do that also in today's class. How do we ascertain that the patch is still working well or is it damaged? So now this is the plot of the root mean square deviation. What we find is that after state number 3, there is a change of slope. So we are able to observe the cracks by the naked eye here, but then from the piezo patches we could sense the occurrence of damage much earlier at state number 4 itself. Okay. Now this is the set of signatures of patch number 1. So patch number 1 is at the beam column junction. So here what happened, that the signatures, they were showing some usual changes, leftward shifting or creation of new peak, something. But then state number 8, at state number 8, there was very upward jump, and then after that it was downward shifting here. So we could see that at 7, sorry, it was not downward shifting. So till state number 6, there were minor changes in the signature. 7 onwards, there was a large identifiable change, and number 8, it was very large change. The cracks were visible here also. The cracks were visible, and they were visible at state number 8. So this is this beam column junction. So here the possible failure, the possible damaged or the crack type, they were shear cracks. So this is the plot of the root mean square deviation, that at this state something we could see the change of the slope, and this indicated that something is serious is happening. So now the thing is that how do we do the diagnostics of the piezo patches, because piezo patches themselves, they may undergo damage. So here the imaginary part of the admittance, the B, that gives us an indication of the condition of the patch itself. So in general, the slope of the B, it remains constant. Even if there is occurrence of damage, the slope basically is capacitive in nature. Slope is a measure of the capacitance part, so it does not change because it is a function of the epsilon 33, the permittivity. But what happens is, if in case there is damage to the patch, that patch may be broken into two parts. Suppose the patch is broken in two parts, then what will happen? What will happen to the capacitance? Will it reduce or increase? Capacitance is directly proportional to the area. So if the patch has broken down into two parts and the connection, so one part is gone out of the scenario, the other part is functioning as part of the circuit, so naturally the capacitance will go down. It will become, say, half. Alright, so that is one condition. Other condition is, let's say the bonding between the patch and the structure has broken down. Then what will happen? It will make the patch behave like a free patch. So this fact is used to identify the type of damage. So any abrupt change in the slope, it indicates something is happening. So here are the example. For example, this line is showing the slope of the piezo patch, bonded piezo patch. So what we find is that slope is more or less constant, even though the peaks they are changing. So in the case of the imaginary part, the peaks are a bit different. They are like Z shape. They go up, then down, and again they merge. So this is the rotated Z shape pattern occurs. So other than that, the slope remains constant. Now in case there is a debonding means now the patch is behaving independent of the structure. So what we'll find that the slope will increase. So the slope will tend towards the slope of the free piezos. So it's a good idea that before we bond the piezos, we acquire their signature in the free condition, so that we know that now our patch, the bonding system is failing. Okay, next thing is that if there is any fracture in the piezo itself, let's say the piezo patch has broken down in two parts. So what will happen is that the capacitance portion will degrade, and this will bring down the slope like this. So these are the two ways we can assess whether the patch itself is fine or not. So we give you example. Now this is example from a fatigue related study we have done on steel joints, and we'll cover this in detail in the forthcoming lectures. So here we are first showing you the real part, the G, and we are seeing that this is undergoing change. So here cycle ratio 0 means that it is the start of the fatigue cycle, and cycle ratio 1 means that now the specimen has failed. So it's a dimensionless, non-dimensional numbering of the cycles. So in between the cycle ratio will vary from 0 to 1. So what we find is that as the cycle ratio is varying from 0 to 1, the signatures, the real part is changing. And let's now have a look at the imaginary part. So imaginary part, do you find any change in the slope? Practically no change. And of course here the peaks, they are not that prominent in the case of the imaginary part, but more or less the slope is constant. So that means that the patch is fine. There is no damage to the patch, or there is no damage to the bonding system. Let's compare another patch. This is example number 2. So here we are showing you the signatures for various cycle ratios. Cycle ratio 0 means we have started the fatigue after this, acquiring this signature, and then as the cycle ratio is increasing from 0.16 to 0.32, 0.51 to 0.71, we are showing you the signatures, and then we have for 0.9 and 1 also. And let's now see the imaginary part. Now what is your observation? See, cycle ratio 0, this was the original B, but then after 0.49 it has come down. After 0.49, when the cycle ratio was 0.99 and 1, we find that it has come down. So what is the reason? What could be the possible reason? So one thing is sure, the diagnostics has failed. But what is the reason here? Is it debonding or is it damage to the piezo patch?
Damage.
Yes, damage to the piezo patch. So naturally the capacitance go down. So that means patch is broken into two parts. So one part is still being part of the circuit because crack. If there is a crack means that one part is lost as far as the electrical circuit is concerned. So everything becomes smaller. So here is a case of the damage to the piezo patch. Let's see another example. So here is again the G part or the real part for various cycle ratios, 0, then 0.53, 0.71, 0.9, 0.32 and 1. And then we show you the imaginary part. So imaginary part, the slope is practically constant. Even if the we are reaching very high number of cycles, even near the failure, there is no change, practically no change in the slope. So that means the diagnostics has been passed. So this sensor has passed the diagnostic test. Alright. So now the EMI technique, the possible applications where the EMI technique is best suitable. We have learned the global vibration technique. We are now in the lab, we are practicing it. You are finding that it's not that simple, though, as it appears in the description. But when you practice it, you find so many problems are there, huge data, you find there is noise, and then you need a human judgment. So many things are there with the global vibration technique. The main point or the main drawback of the global vibration technique is that it is suitable for moderate to severe damage. When the damage level is low, then the global vibration technique is not that good. So EMI technique can substitute the global vibration technique where we have this kind of precarious situation where we want to identify the damage at very incipient stage, or if the member is very critical, small, because this has a small zone of influence, so it's particularly good for those regions which are inaccessible. So basically here, for example, in the case of the bridge, these regions like the hanger pins, they are very much affected by corrosion. So the EMI technique is quite good for this kind of situations. It's also good for aerospace structures which are small in size. So these are potential areas of application of the EMI technique. So we'll see more in the forthcoming lectures how the EMI technique can complement the global vibration techniques. So in the next two lectures will involve something on the theory part, because right now what we have given you is a picture of the EMI technique, picture in the sense that how it works, but then the theoretical background and some other important understanding related concepts we'll be studying in the next two lectures. So the next two lectures, they will not use the slides. We'll be using the tablet pen and you will have to make hand notes. Alright. So any doubt on the EMI technique, what we have learned? So we have here some reading material also. So what the case studies, what we have seen is that the EMI technique captures incipient damage before human eye can do so, and this is different from the global vibration technique, so it's an advantage. And then the damage zone is localized, so this gives us the potential for damage localization, means finding out where the damage has occurred. So it's suitable for civil structures, but then it has a drawback that it's very good for the incipient damage, but then when the damage level increases, then we get some sort of plateau, which can be confusing in nature. So we'll study in the forthcoming lectures how we can overcome these problems, because as engineers we always have a trade-off kind of thing, that we have certain thing which is good for certain situations and may not be perfect for all situations. So we have to optimally use every sensor or every technique to our best advantage. So I think now we can have some questions before we go to the minor paper. Okay, any question? Aniket Vishwas is raising hand. Yes, Aniket.
I have a question, sir. I love.
Okay, so I think Dr. Dhawan has the first. Let Dr. Dhawan ask question first. Your camera is positioned incorrectly. Your hair is visible. Yeah, now.
Now, I'm also visible.
Yes.
See, the question that comes mind, the PGT patch we use as sensor. And then we have to see that any sensor that put, we should think of the life of sectors, 50 years, 60 years. What is the life of such sensors that we are using here in our EMI technique? Life of sensors.
Life of sensors, if you are protecting the sensors, protecting from the damage. See, lead zirconate titrate in general, it is a chemically inert, more or less chemically inert substance. So if you are protecting it, so what is the possible damage to the sensor is, let's say if the sensor is heated above the Curie temperature. So all the manufacturers, they specify a Curie temperature. So if you are subjecting it to very high temperature fluctuations, that may damage the sensor. Other potential damage is under very high electric field. Because in the manufacturing process, the manufacturers, they use a process called polling. So they apply a high electric field during the process. So that imparts a permanent dipole moment to the material. So if we are subjecting the patch to very high electric field, that may again depole the patch. So if these two precautions are taken care, then I don't think there is anything with the life of the piezo patch. If we are using, in the case of the concrete vibration sensor, they are inserted inside, and I don't think there is any damage. They can work for years and decades and so on, 30, 40, 50 years. In my case, I still have my sensor which I used during the PhD, and that sensor was installed in the year 2001. In the year 2001, and now it's 2022. So that sensor is still working after 20 years. And there is nothing, no problem I find in the working of the sensor, because these sensors, they have very negligible aging rate, very negligible. So they can last for years and years. And even if, let's say, there is a damage to the sensor, we can always replace that. Some sensors may undergo damage because if there are cracks which are just passing through the piezo patch. So in case of any damage, if for example the piezo patch is surface bonded, there may be some damage, so those sensors, they can be replaced also.